Hi, in this video, we're going to talk about sum and difference identities, section 3 of chapter 5. The practice problems for this section will be page 425, 11 through 14, page 426, 17 through 19, and 23 through 28, skip 24. So, what are the sum and difference identities and how do we use them? First of all, I would like to tell you that those sum and difference identities are in your identity sheet. Personalized one, if you want to take a look at the personalized identity sheet, those will be identity 26. So, this one, which is cosine, will be identity 26. This one will be identity 27. The sign will be identity 28. And this will be identity 29. So they're a little bit in a different order and they do use different angle. So instead of A and B, we use X and Y in the personalized identity. You can use theta and alpha. You can use any two letters to refer to the two angles. And this is identity 30 and this is 31. Notice that in your personalized identity sheet, you see 30A and B, 31A and B. We will discuss 30, 31, both parts A and B in a separate video. So this video is going to focus on the first four. First of all, when we say sum and difference, A and B are both angles in all the four identities. Sum and difference identity, here we see a plus, here we see a minus. That's why it's sum and difference. Let's take an example right away to prove how useful those identities are. So I'm going to start with an example that is asking me to find the cosine of 75 degrees. So I'm going to find the cosine of 75 degrees. If I look at the unit circle, which is on the next slide, if I look at the unit circle, I won't find 75 degrees as a remarkable angle. So let's take a look. When we say remarkable, it simply means it's on the unit circle. So if I look at my unit circle, I don't see 75 degrees as remarkable. I see 30, 45, 60, and so on. So that's why in order for me to find the cosine of 30 degrees, 75 degrees, I need to split it into 30 degrees and 45 degrees. Why is that a combination, just 30 and 45? There is a reason. So if we if we split 75 degrees into 30 and 45, and again, why is that combination not 25 and 50, for example? Because 25 and 50 are still not remarkable angles on the unit circle. Versus 30 and 45, they both exist on the unit circle, so I can find the cosine of both of them without the use of a calculator. So I look at this and say, which identity does it match? And I'm going to go back and write the identity 26, 27. Those are the ones we'll be using, 28 and 29 for today. So I look at this, which one does it look like? It's a cosine, so it's either one of these. It has a plus, so it's definitely identity 26. So I apply it. Cosine A, cosine B, minus sine A, sine B. A and B are the angles. A is the first angle, B is the second. So cosine of the first times the cosine of the second angle in degrees minus sine first sine of the second angle equals. Do I know what's the cosine of 30 degrees? Yes, we do. If we go back to our unit circle, we can figure out that the cosine of 30 degrees is square root of 3 over 2. Do we know what's the cosine of 45 degrees? Yes, we do. Do we know the sine of 30 and sine of 45? Yes, we do know both. So that's why we are able to find the cosine of 75 degrees using the sine and cosine of 30 and 45. So I'm going to fill this in. Square root of 2 over 2 and minus the sine of 30 degrees is half and the sine of 45 is square root of 2 over 2. Multiplying fractions, I multiply numerator by numerator, denominator by denominator, and same for the second term. And I can write this using the same denominator, which is square root of 6 minus square root of 2 over 4. So that is the radical form. I don't need to get a decimal approximation unless the question asks me to do that. If I put cosine of 75 degree on the calculator, I'm going to get the decimal answer. This is the specific exact solution. I can factor out square root of 2 and I'll be left with the square root of 3 minus 1 over 4. And that will be the answer to cosine of 75 degrees. Now, I really want to show you one example that proves that this identity is correct. And I like this example because we know it ahead. So we all know that the cosine of 90 degrees is 0. And you can tell by looking at your unit circle. The cosine of 90 degree. Here's 90 degree. The cosine, which is the x-coordinate, is 0. So we confirm that. Let's go back and try to find cosine of 90 degrees using the sum and difference identity. So I'm going to split 90 degrees into 30 and 60. Can I split it into 45 and 45? Of course. Can I split it into 20 and 70? You can, but you won't be able to use the unit circle because 20 and 70 are not remarkable. So I'm going to apply the same identity, which is identity 26. So cosine, cosine minus sine, sine. Sine of the first, sine of the second. And degree signs and all of them. Do we know the cosine of 30 degree? Yes, we do. We just used it. If I look at my unit circle, which is on the next slide, cosine of 60 is half. Sine of 30 degrees also, we just used it in this problem. And sine of 60 degrees, which is square root of 3 over 2. If I look at this, I can tell that this quantity is the same exact thing as this quantity, and the result will be 0. And this is definitely true. Cosine of 90 degree equals 0. Now let's apply an example with sine. So let's change the color, and we'll take sine of 90 degrees, which also I can split it into 30 and 60. And if we look at our unit circle, we know that sine of 90 degrees equals 1. And that's again by referring to our unit circle. Let's prove that this is true. I look at this, and which identity does it look like? It looks like identity 28. So for identity 28, it's sine cosine plus cosine sine. So sine cosine and then plus cosine sine. The setup is a little bit different from the cosine one. So we know the sine of 30 degrees, we just used it. We know the cosine of 60, the cosine of 30 degrees, and the sine of 60 degrees. So half times half gives us a fourth. Square root of 3 times a square root of 3 gives us a 3. 2 times 2 is a 4. A fourth and 3/4. 3/4 will give us 1. And we proved that sine of 90 degrees equal 1. The last example we're doing in this video just gonna erase this part, is gonna be a quick proof. So in the previous section, which is section 5.2, we did proofs. This one is a very small proof, but using the sum and difference identities, and also using the unit circle. So when we use sum and difference identities, we do need to use the unit circle because mainly we're not using the calculator, because the calculator won't give us the exact value of sine and cosine of the non-remarkable angles. And again, non-remarkable angles are angles that are not on the unit circle. So let's take a look at our example. Prove that the cosine of x plus pi over 2 equals negative sine x. If you look at your personalized identity sheet, this is one of the identities, and it's one of the co-function identities, more specifically. And this will be identity number 15, very similar to it, except that 15 has a subtraction and this one has an addition. So let's take a look at this. Which one does it look like? It's a cosine. So that's the number one step we would like to do. Cosine, and there's a plus. So this is identity 26. It's a sum identity. So I'm going to split it into cosine. So I'm only working with the left side now. So cosine x times cosine b, so b is the second angle, which is pi over 2, and minus sine x sine pi over 2. Let's take a look at this. So one thing you need to know is that the cosine of pi over 2 is 0, and we saw that on the unit circle. Sine of pi over 2 is 1. We also saw that on the unit circle. So 0 times cosine x, this term is gone. 1 times sine x is just sine x. And don't forget there's a minus here that we would drag it down. And we proved it in one step using identity 26, which is sum and difference identity. So now it's your turn to apply the sum and difference identities to the practice problems listed in this video right under the title.